Scikit-Learn. So, which is a popular machine learning toolkit. Okay, it includes the NumPy, SciPy, and Scikit-Learn. Okay, so all these, which are see, NumPy and SciPy are necessary for the Scikit-Learn. Okay, we'll discuss it is work which is learned over the basic. So Scikit-Learn is also known as sklearn. It is an open source. This library enables the practitioners to rapidly implement a vast range of supervised and unsupervised machine learning algorithms through a consistent interface. So sklearn was built on top of the SciPy and works on all types of numerical data stores as either NumPy arrays or SciPy sparse matrices. So, and all other data types that we converted into the numerical arrays like pandas, data frames. So, while we are learning the scikit-learn, we should know most of the NumPy and SciPy. Okay, and SciPy, see that you can learn parallelly. Anyways, I am going to give you brief introduction about the SciPy also. So, anyways, we are going to give the same scikit-learn examples. Still, we will have a SciPy introduction also. So, coming to the SciPy, again, it's an open source Python library used for scientific computing and technical computing. It builds upon a NumPy library, providing the wide range of modules for tasks such as optimization, integration, interpolation, linear algebra, and signal processing and image processing and statistical methods. Okay, so this SciPy, if you learn this, if you are very good at this SciPy, you can easily learn the what we are saying the scikit-learn as well. So SciPy is at the end, SciPy is a open source library. Okay, like we can use the first thing like SciPy stat. This is the main public method for a continuous random variable or random. It is a continuous method like SciPy stat. Okay, or like random variables or probability density function or cumulative distribution function. Okay, so function. There are different functions which are supported by the SciPy stack. Okay, like that, the SciPy is is very good library for implementing the statistical, and it will work over the what we call this NumPy. So let me okay. So using the pip install the SciPy, okay, I have installed the SciPy. Okay, it's installed the SciPy package 1.16.2. Okay, we are working on it. So we have installed the SciPy. Okay, and we have once we install, we can import SciPy modules. We can add any mod using the like from SciPy. We can import any module. Now we have imported the constant modules from SciPy. and apply, and we can use those constants. Okay, so like here we have what we did. We have printed. We are printing the. We are downloading the constant, right? Say simply we can use the print constant space lighter. Using that, we can get we can print the constant dot lighter value over there. Okay, like that, a simple constant were downloaded. Okay, and if you want to know, uh, if you want to know the version, simply you can use the sci-fi. Okay, in the command prompt, you can use this sci-fi. We have already installed the sci-fi, but it is saying sci-fi is not defined. Uh, so the another is sci-fi constant. So as sci-fi is more focused in scientific implementation, it provides many built-in scientific constants. Okay, as we said, if you want to see the pi, okay, simply instead of a liter, you can use print pi. So, so the pi value is given by the sci-fi. So because the mostly this sci-fi is for the scientific constant, we can it already using the from sci-fi as we have done here from sci-fi import constant. So we have imported the all the constants which are used, which are mostly used in the sci-fi. So if you want to list all the units, all the units which are used in the this constant, then we can simply use print dice, okay, and constant. So you can see these are the different constants, okay, which can be used for our scientific application. Sigma, stone, trion, data, Devi, beta, zero, cell, all these are the different constants as we have downloaded the pi over here. So we can use the Python, okay. So and we can have different categories as metric, primary, uh, mass, okay, mass and angle, time, length, pressure, volume. These are the different categories for this units or a directory. All the type a constant. Okay. Then the another important category of SciPy is optimizers. So optimizers are a set of procedures defined in SciPy that either find the maximum value of a function or the root of a equation. Okay, so optimizers are a set of procedures defined in SciPy that either find a maximum value of function. So essentially, all maximum value of a function or the root of each equation. So essentially, all of the algorithms in machine learning are nothing more than a complex equation, right? So when we are using machine learning algorithms, all of them are a complex equation that need to be minimized with the help of given data, right? So that is optimizing this optimizing of these equations can be done by the cycle. So NumPy is capable of finding the roots of polynomials and linear equations, but it cannot find the roots of nonlinear equations like x plus cos x. Okay, for that we need to use the SciPy. So using the NumPy, we can find the roots of polynomials and linear equations. But coming to the SciPy, we need for nonlinear equation like x plus cos x, we need this SciPy. Okay, so for that we can use optimized root function. Okay, the function is representing an equation, and x0 is an initial guess for the var. So here we'll take an example. Say from the scikit optimize. The second thing we need to discuss is scikit optimize. Okay, so this scikit optimize is we use, okay, which will optimize the nonlinear equation. Okay, to find the roots of a nonlinear equation, we use this. So from the math import cost, say we are defining. So we are defining a function equation which takes the x, which returns the x plus cos x. Okay, and my root is root of this equation. My root is root of this equation. It will find the roots of a nonlinear. Okay, so as you all of you know, I think all of you are good at this nonlinear equations, linear equations, and finding the roots. Okay, for polynomials and linear equations, you should be knowing those things. Otherwise, just go through them. Okay, so here for this by sending, so from so it is saying scalar is duplicated. Conversion of an array with ndim greater than to a scalar is duplicated, and the error will error in future, and ensure extract single element. So that is it is saying it is a what we call suggestion it is giving. So here we have printed the root for this equation. We have printed the root for this equation, right? So like that, to find a root, we can use this SciPy. Okay. Uh, so here, proofal information about the solution does not just text which is not root. Then this is an optimization, finding a roots for equations. Second function is another method, another feature is sparse data. So sparse data is a data that has mostly unused elements. When we talk about sparse data, it's a data which has the mostly unused elements. So it can be an array like this one, like if I show you some array series, I'm printing an array. One. So here the problem is it has mostly unused elements. Okay. So the data set, it is a data set that where the most of items values are zero. Here you can see only 3 times the values are 1, 2, 3. The other cases all are 0. That we call as sparse data. Okay, this we call as sparse data. This is sparse data. Another category is dense data. Dense data is which has more less zeros and which has less zeros and most values that we call as dense data. So dense array or dense data is opposite to the sparse array, in which the most values are not zeros. So in scientific computing, when we are dealing with the partial derivatives in a linear algebra, we'll come across this sparse data. So SciPy has a module like SciPy sparse that provides the functions to deal with the sparse data. Sparse data means, as I said, it has most zeros. These are primarily two types of sparse matrices that we can use: CSC, uh, CSC, CSC. So that is compressed sparse column for efficient arithmetic, large column slicing, and CSR, that is compressed sparse row for fast row strong. So these are the different sparse uh, functions. Okay, so but in that we use the two matrices. They are called as, so first one is the CSC, compressed sparse column. This one matrix which is used in the sparse module of this SciPy. Another one is compressed sparse row for for a fast row slicing. We use the faster matrix product. So in both the cases, these are the both columns mostly used when we work on this sparse matrices or sparse data. So first we'll create SciPy sparse, and then we'll print this. Say we are importing the numpy as NP, and we are using the sparse module to import the CSR matrix. Okay, row CSR matrix. So what we did using the SciPy, we have a SciPy module path. We have imported the CSR underscore matrix, CSR underscore matrix, and we are creating an array as with zeros sparse data. Okay, mostly zeros are there. You can see, and in this, you, they are passing this to the CSR matrix. Okay, which returns, you can observe the output. Okay, so it compressed the sparse row matrix. Okay, with the three stored elements uh, and shape of 1 to 9. Okay, so if you print this, so what happened? So it, all the rows you can observe here, we can see there are three items with value. Okay, the first item is in row 0 position, and 5 has the value of 1. Position 5, the item is in 0, row 0, position 5 has a value of 1. The item of row 0, position 6 has the value of 1. And so that is, so the same, you can see array whatever we have taken, 0, 0, 0, 0, 1, 1, 0, 2. That is the array we have taken, right? So that we are converting into the CSR matrix. Item in row 0, position 8 has the value 2. So that is the last row. So item in row 0 and position 5 has 1. So what we are doing, we are eliminating the 0 value, unnecessary values. We are only simply managing the position coordinate as well as those coordinate values. Instead of maintaining all these zeros, the sparse data, we are only specifying these values, okay, by using converting that into the CSR matrix, like using the coordinates and values. So when did we when we got this is the zeroth row and fifth position, right? Has a one, and this is the zeroth row, sixth position, okay, has another one, and this two is in the zeroth row and eighth position, right? So like that, we are converting that using the CSR underscore matrix. We are compressing the data using the SciPy sparse. Okay, it is mostly useful when we are having huge data with more zeros. Okay, so we can also use. Say, I'll give you another data, like to observe this data, right? If we print this data, so we have most zeros, right? It is in the column matrix model, right? Say if we want to print the CSR matrix, okay, and array. So initially we have used the CSR matrix of array. Uh, if we say if we are printing the same, you can see the row one and second position is having one, row two zero position is having the one, and row two and two position is having the two. So if you want to see the data also, we can see the data. So here we are not showing unnecessary all these zeros. These zeros, we are only talking about the values in the matrix. That that is useful while we define a sparse data. Okay. So we are managing the sparse data here. It is only giving this 112. So it is nullifying all the zeros, and it is only showing the values which are dense, which are useful. It is not showing the zero. So to manage the sparse data, we can use the SciPy. Okay, and we can also count the non-zeros using the uh, non-zero count underscore non-zero method. Okay, so we have it is counting the non-zero method, as well as we can remove the zero entries from the matrix using the this CS this ma simply using the eliminate underscore zeros. Using the eliminate underscore zeros, we can, so here you can see CSR matrix array is given to the matrix, and using the eliminate zeros, we can eliminate the zeros in matrix, and we can only print the matrix. So here we have eliminated and we have printed only the zero. And we can also eliminate the duplicate entries by removing the some duplicate, removing with the some duplicate. So this is one method where we remove the duplicate. Okay. So like this, we can remove the duplicate, and we can also count from CSR. We can convert the CSR to CSC using the two CSC method. Okay, that we can do by simply, then I'll do the input. using the 2 CSV. So using the 2 CSR matrix of array, 2 CSV will convert the rows into CSR, CS rows into the compressed sparse row into the compressed sparse column. Okay, we can convert like that, and we will see what is the output. So compressed sparse column, using that we have converted, and we are representing instead of rows, we are representing with the column. So that's it about the sparse data, working with the sparse data. Okay, we can also work with SciPy graphs. So SciPy graphs comes with a module called SciPy sparse CS graph. Okay, so normally SciPy graphs are represented. Graphs are graphs are essential data structure, and SciPy provides with the module SciPy sparse.cs graph for working for such data structure like adjacency matrix. Okay, so adjacency matrix is an n into n matrix where n is the number of elements in graph and the values are represented as a connection between the elements. Like if it is A, B, C, adjacency matrix, right? If A is connected with B and with the value 1, we'll draw a line to AB, and in between 1 will be there. So say I'll try to present an adjacency matrix. I hope you should know adjacency matrix. Otherwise, let me show you, unshare, and in the Google image, I'll show you. So this is an adjacency matrix where you can see these are the nodes. I try to increase the size. So from this node to this node, this node to this node, connections are there. Okay. So when connection is there, say we will represent that with the 1, 2, 3, 4 matrix. Okay. And they are simple label graph of a matrix with rows and columns labeled by graph itself with 1 or 0 position, say from Vi to Vj, according to the if we have an adjacent or not. If we have the adjacency, we will represent that with the 1. If we don't have the adjacency, we will represent that with the 0. Let me see here the graph. We have 0, 1, 2, 3, right? So for that, we'll create a matrix. Okay. So 0, 1, 2, 3, 0, 1, 2, 3. Do we have a connection between 0 and 0? No. So it is represented with the 0. So if we have, do we have connection between 0 and 1? Yes, we have. So it is represented with the 1. Do we have connection between 0 and 2? No. It is represented by 0. We have connection between 0 and 3? No. It is represented by the 0. Right? So do we have connection between 1 and 0? 1 and 0 connection is there. So it is represented by 1. And do we have connection between 1 and 1? No. So it is represented by 0. Do we have connection between 1 and 2? So 1 row and 2 columns. So there is a connection. So it is represented by 1. So that's what we call it as an adjacency matrix. Okay. So it's an undirected and unweighted graph. We may have the directed and weighted graphs also. Okay? Like it is undirected and unweighted. It is a weighted. So instead of zeros and ones, it represents the values over there. So 0 to 1, 0 to 1, 5. It's a undirected and weighted graph. There will be directed and unweighted graph, and directed and weighted graph also will be there. So only one side only we will calculate here in the matrix. That we call as adjacency matrix. Okay. I hope you understood adjacency matrix. So we are talking about this graph. Okay. So say we have an adjacency matrix like using the how we represent using the directed or depending upon directed or undirected and a weighted graph. Based on that, we will represent that with a matrix. So for that, we'll import connected components method. We'll import in the this SciPy. We'll import the in, using SciPy sparse CS graph. We'll import connected components and we'll import the CSR matrix. Okay. So using that, okay, say we can create, we can work on the any array as an adjacent matrix. So I hope you should know what is this extra and all to work to learn about it. So, so what it is showing? It is showing the connected component. Okay, in the new array. In this from above matrix, it is showing the connected component. So we are showing here. So this shows the CSR matrix of array. So it is removing the zeros, and after removing the zeros, it is printing the connected component. And say if you want to use a Dijkstra method to find the shortest path of a graph from one element to another, will it takes the arguments and uses here using this uh, SciPy, we can use the Dijkstra method to find the shortest path, and we can also use the flight Warshall. So this we should know what is Dijkstra method. When we are using a adjacency matrix to find the shortest method from one place to shortest path from element 1 to 2. Say if I am representing an array called an adjacent matrix, I'm creating an adjacency matrix. Okay, so this matrix shows the graph, right? We have how many nodes here? We have 3 nodes, 0, 1, 2, right? Uh, so we have 3 nodes, 0, 1, 2, and we are finding the adjacency using this. So here what it means from 0 to 1, there is a path with weight 1. And from 0 to 2, we have a path with weight 2. From 0 to 0, there is a path 1 to 0, there is a path with weight 1. And from 2 to 0, there is a path with weight 2, right? So you want to find a path between the 1 and 2, the shortest path between the 1 and 2. So uh, in the next class, I'll try to, because the diagrams are to be represented, I'll try to draw them and explain that concept. So using the Dijkstra, we can find a shortest method. Okay, for that we can say it can use the return predecessor, indices, and limits. Okay, so using that we can find a, for that first of all we need to create non-zero values. There is no path we need not to we need not to use the non-zeros. And we need not to use the zeros because zeros only represent that there is no path, right? When here we are using the CSR matrix, which gives us only the when there is non-zero value. That means there is a path between the in that position. That position. If I bring like this, so from in the 0 and 1 coordinate, from 0 to 1, a path is there. 0 to 2, a path is there with the value 2. From 1 to 0, there is a path with value 1. From 2 to 0, a path is there with value 1, right? So here we need to find the represent the discussor also. For that, we need to use the uh, discussor. We need to download the discussor. That is the reason it is showing there. So from SciPy Spark import discussor, using that we are specifying the return predecessor true and indices, and we are finding the shortest path. We are finding the shortest path from 1 to 2. So use here you can see. So this is for new array, which shows us the different paths available. Okay, and the shortest path is 0, 1, 2. Okay, that's how it is representing the shortest path. So here we have used the we have used the shortest path which is represented by the disjunction from one element to the other. So for that you need to know what is disjunction, what is slide Warshall, what is Bellman Ford, and what is depth first order, what is breadth first order to find the shortest path. So as you know, breadth first orders and BFS and DFS and what is this Bellman Ford, what is this Clyde Warshall, what is discussed. It is very important for in the robotics to find the shortest path. Nowadays, we are working on the different categories of different, more advanced shortest path algorithm. But uh, so we'll discuss all those in the Scikit-Learn and all. So today we have discussed the SciPy, which is a basic for the Scikit-Learn, and NumPy we have discussed, and Pandas we have discussed, which are basic for the what we call Scikit-Learn. So using the Scikit, again, when we are learning the Scikit, parallelly we have to implement different supervised algorithms, unsupervised algorithms, okay, and reinforcement algorithm. So that we need to implement while implementing learning the Scikit. So for that, better we understand what is supervised, unsupervised, and reinforcement algorithms in machine learning. So tomorrow, or not tomorrow, day after tomorrow, please go through those algorithms. Day after tomorrow, we'll discuss few supervised, one unsupervised, and one reinforcement learning basic algorithm. Then we'll go further. Supervised having many algorithms, unsupervised having many algorithms. At least we will discuss four main algorithms, and we'll try to implement that with the Scikit-Learn. Then we can go for the deep learning concepts where we'll use the other libraries like TensorFlow and all. So that's it about what today. Just let me brief the Python Scikit-Learn algorithm. Just